Hey everybody. So now that the fire alarm has stopped, well actually I moved locations so I wouldn't burn down with the building. Um, but what is the probability of that happening? What I wanted to do is finish the lecture and finish our discussion of that probability mass function problem. So let's kind of remind ourselves where we were at and get this thing going. Okay, so remember we were looking at the joint PMF of midterm scores, and we had a series of midterm scores, and we also had standing associated with each student. And so we were supposed to prepare a joint PMF of the data, which we accomplished. Then we were supposed to prepare a joint CDF, which we haven't yet done. And then also to look at marginal distributions for the two random variables, which in this case include score as well as class standing. And then we were asked to determine what is the interpretation of these marginal distributions. And just as the fire alarm was ringing and everybody was running out of the building, we were basically looking at sort of part C. So anyway, I want to pick it up. Maybe kind of return to part C again, just to kind of remind ourselves of what we did. And then come back to part B and then finish this problem setup. Okay, so let's go to the Excel spreadsheet and have a look. Okay, remember we had basically pairs of midterm scores and standings, and we sorted these guys by midterm scores and counted the number of sophomores, juniors, and seniors that received a particular score range, and then filled out this frequency table. And so basically we had a total of 99 students. We divided 99 into all of these numbers to get the probability mass function for this distribution, which basically says for each row here we've got a different score range, 20 to 40, 40 to 60, 60 to 80, and 80 to 125. And then the columns denote sophomore, junior, and senior standing. And then we were calculating the marginal probabilities. And again, the reason it's marginal is it's around the margins, right? So the marginal probability for standing was just the sum over all scores for sophomores, juniors, and seniors, and those the marginal scores for or probabilities for standing are indicated, highlighted in yellow here. And so we know that about 27% of the students who took the exam were sophomores, 54% were juniors, and about 19% were seniors. Likewise, we could calculate the marginal distribution for scores, in which case we're summing across all of the different, I'll just highlight this, we're summing across all of the different standing for each score level. And so when we do that, we get the green marginal distribution here. So about 9% of the test takers got between 20 and 40, about 24% got between 40 and 60, 36% got between 60 and 80, and 30% got between 80 and 125. Okay, and the other thing is that if we sum down this column, we would get 1, and if we summed across this column, we would get 1, which makes sense because these are marginal PDFs or PMFs actually, so they should sum to 1 if we sum up all the area under them. Okay, so that's the probability mass function and the marginal distributions for the probability mass function and kind of what the physical interpretation of those marginal distributions are. So hopefully that now really makes crystal clear sense. We were kind of coming back to I think we jumped when we calculated the marginal distributions, we kind of skipped a question. Coming back to the question that we skipped, basically we were supposed to calculate a CDF from the PMF for scores and standing. And remember what we do for the CDF when we're talking about a joint probability mass function is that we basically sum over all random variables that are less than or equal to a particular value of xi and yi or yj. So in this case, we're starting up here in the score range 20 to 40 and sophomore. Basically, this is kind of in the 1-1 position. So there is really no nothing to sum, so we just basically take over the value from the PMF and move it straight into the CDF in this position. If we come down the sophomore level, so we can move to this cell here, basically for the CDF, the value in this 40 to 80 range is going to be all of the probability associated with getting, for sophomores, getting a score in the 40, well, really the score of 60 or smaller. So that would be the sum then, and let me see if I can just kind of highlight and show you. So yeah, so it's the sum of the score for 40 to 60 and the score for 20 to 40 for sophomores. So that's going to be the value in the CDF at this location. If we come down here to the score for 60 to 80, basically the CDF is telling us the probability that sophomores scored a score of 80 or smaller. And so that means we're going to have to sum the probabilities for scores running from 80 on down to 20. Okay, so that's where that comes from. And then finally, for the CDF position of sophomores and with a score of 80 to 125, we're really asking, what probability or what percentage of the students scored, sophomore students scored a score of 125 or smaller. And we sort of sum all that up, and we find that it's 27%. And interestingly enough, that's equal to the marginal probability for standing for sophomores. And that was kind of one of the characteristics of CDFs, one of the features of CDFs that we talked about earlier. Okay, so you got that idea, and then we could do the same thing across, just the 20 to 40 row here. So for juniors, basically we're asking for juniors or sophomores, what is the probability that they scored in the 20 to 40 range? It's just going to be the sum of these two cells, and that's about 9%. And then if we went over here, we're basically summing over sophomore, juniors, and seniors. Basically these are the same because seniors, there were no seniors that scored 20 to 40. And maybe it's a little bit more tricky if we come into this cell here. So basically here we're asking, among juniors or lower standing, what is the probability that students who will get a 60 or less if they're junior or sophomore, right? I guess that's exactly. And so that's going to be the sum then of the scores in this blue box, basically going from sophomores and juniors scores from 20 to 60. To put that a little bit more succinctly, I guess that you could say it's the probability that you get a score of 60 or smaller given you were a junior or a senior. And likewise for this cell, we could basically ask, what is the probability that you'll get a score of 80 or smaller if you were a junior or a sophomore? And it's going to be the sum over all of these cells. And we keep playing that game. Let's come over to this one. So this is the cell where we're asking the question, what is the probability you'll get a score of 80 or smaller given that you're a senior, junior, or sophomore? And so that's going to be the sum over these cells given in the blue box. And then finally, if we get to the point where we're asking, what is the probability that you're going to get a score of 125 or smaller if you were a sophomore, junior, or senior? Well, that's the entire class, and that's the entire score range, so the probability has to be 1. So this definitely matches the limit, the upper limit of a CDF, which ultimately asymptotes to unity. And then also we don't go to 0 here because this is a PMF, and there is no such thing as a 0 score or student with no class standing, right? But you can see that in this far upper left corner here, we have very low probability all the way to the complete, 100% probability in the lower right corner. Okay, so that's the CDF. I think it was like the fourth question asked us to compute conditional probabilities. And really, we were supposed to compute those conditional probabilities in 2 different ways. we were supposed to compute the conditional probability of the scores conditioned on standing as a sophomore, junior, or senior. And then we were also supposed to compute the conditional probability of standing conditioned on scores. So whether it's 20 to 40, 40 to 60, 60 to 80, or 80 to 120. So basically that's what I've done here. Let's start with the conditional of scores conditioned on sophomore standing. So how do we do that? Well, basically, for each of these scores, the score ranges 20, 40, 40, 60, 60 to 80, and 80 to 125. For each of these score ranges, what I'm going to do is I'm going to compute the probability that sophomores, I'm going to compute or look up the probability of that score range for sophomores, which is 0.04. And I'm going to divide it by the marginal probability for sophomores, which is the yellow 0.27. So if you open up that equation, basically it's taking that probability for sophomores getting in the 20 to 40 range, and then just dividing it by the marginal probability for sophomores. And so what we're asking in this particular case for sort of physically or conceptually is we're saying just among sophomores, what was, if you just consider sophomores alone, what was the probability they got 20 to 40, 40 to 60, 60 to 80, or 80 to 125 score range? And so what we see is that the sophomores, basically of the sophomores, about 15% got 20 to 40 and 40 to 60. About 30% got 60 to 80, and about 41% got 80 to 125. So they were doing pretty well, actually. And then we could compute similar conditional probabilities for the juniors. So now we're looking at just the, we're just going to focus on only juniors. And so this is a conditional probability on juniors. So we're going to take each of these scores that juniors had in each of the categories and divide by the marginal probability for juniors, which is 54%. And so in that case, we find that among juniors, about 9% scored 20 to 40, 25% scored 40 to 60, 42% scored 60 to 80, that's there, and about 25% scored 80 to 125. So it's kind of, it's a little bit different than we saw for the sophomores. And likewise, for the seniors, we basically look at their scores and then divide by the marginal probability for seniors. And we find that 0%, we already talked about this, scored in the 20 to 40 range because they were eager to graduate. About 37% scored in the 40 to 60, 32% scored in the 60 to 80 range, and 32% scored in the 80 to 125 range. So, so that's what the marginal probabilities, I'm sorry, not the marginal, the conditional probabilities of scores conditioned on standing would tell you about the test. Conversely, we could ask, what is the standing conditioned on score? So of people, so basically what we're asking here is, of the people who got a score in the range of 20 to 40, how many of them were sophomore, juniors, and seniors? And so how do we compute that? We basically take the percentage or the probability of sophomores getting a 20 to 40, and we normalize it by, oops, better not actually run that. We normalize it by the marginal probability for the score. In other words, the percentage of people who got that score of 20 to 40. And so what we find then is that of people who got scores in the 20 to 40 range, about 44% were sophomores, and about 56% were juniors, and 0 were seniors. Likewise, we could look at the standing conditioned on getting a score of 40 to 60. And so again, if we sort of open that up, we're going to see that what we're doing is we're calculating for sophomores the probability that they got a score in the 40 to 60 range, normalized by the marginal probability for that particular score range, which is 24%. And so what we see is that for people who got a score of 40 to 60, about 17% were sophomores, 54% were juniors, and 29% were seniors. And so we can play similar games for these other scores. Let's just go to this last one because that's kind of interesting. So of the people who got the highest scores, 80 to 120, how do we calculate that conditional probability? Again, we go for sophomores getting a score of 80 to 125, and then normalizing by the marginal probability associated with that score. So we get that about 37% of the people who were getting scores of 80 to 120 were sophomores. So those guys were rocking. 43% were juniors. That's even better. So you can see they're juniors here. And then 20% were seniors. So, so that basically explains the conditional probability. And the last thing that I want to calculate has to do with determining whether standing and a score were statistically independent random variables or non-statistically independent random variables. So let's look back at, so just for a minute, let me kind of click out of the Excel sheet and click into our problem statement again. Okay, so here's a problem statement. And so basically we're interested now finally in part E, are the scores and standing random variables, are those random variables independent or dependent? And one way that, just kind of backing up a minute, one way that we can assess that is through the covariance between those two random variables. And let me just kind of go to the point where we calculate covariance for a discrete PMF. So remember, this is the definition for the covariance between two random variables, x and y, for a discrete PMF. And so basically what you can see is it's the sum over all of the xi and yj of the product of xi subtracting out the mean for x, yj subtracting out the mean for y, and then weighting by the probability. So that means that one way to compute the covariance is to create a matrix in which basically for every xi and yj, we compute this quantity here. And then when we're done preparing that covariance matrix, we just sum over all the cells to get the total covariance. And so each of those cells of the covariance matrix is going to be constructed by first determining what the mean of the random variable x is, the mean of the random variable y, and then subtracting the xi and the yj from those respective means and weighting them by the corresponding probability. Okay, so with that in mind, let's go prepare the covariance matrix. So again, I have to shut off the screen share, or at least move it over to the Excel spreadsheet. Okay, so the first thing I need to do is compute the mean of standing and the mean of score. And here is where I need to use those numerical substitutes for standing. And so remember, I told you, I think earlier, that I arbitrarily defined sophomores as a number 2, juniors as a number 3, and seniors as a number 4, right? So I have a numerical score associated with the standing. And that means that I can compute the mean of standing. How do I do that? Basically, what I do is I look at the marginal probabilities for standing. So I've got 27% of the students were sophomores, 54% were juniors, and about 19% were seniors, right? So what I can do is to compute the mean is I can weight the score that I gave each of these class standings by their corresponding probability. So that means I would multiply the probability 0.27 into 2 for sophomore plus the probability 0.54 for juniors into, or multiply that into 3 plus the probability for seniors 0.19 into the corresponding number for seniors 4, and I would sum those up. And so let's see if that's what I did for calculating the mean here. Basically, you can see, yep, I took the score for sophomores 2 times the marginal probability for sophomores plus 3 times the marginal probability for juniors plus 4 times the marginal probability for seniors. So that's my mean for standing. I also have to calculate a mean for the score across all of these tests. And here I can do a very similar thing. I've got the marginal probabilities for the scores. So I know that 9% of the test takers had a score in the 20 to 40 range, and then 24 had a score in the 40 to 60 range, and so forth. So all I have to do is basically assign a specific number to those ranges, and I might as well take kind of the midpoint. So I'm going to take, for 20 to 40, I'm going to say that's a score of 30, and I'm going to multiply it by the appropriate probability, which is 0.09. And then I'm going to take the midpoint between 40 and 60, and that's, of course, 50. And I'm going to multiply it by the corresponding probability, 0.24, and so forth and so on. And so let's see if that's what I did to calculate my mean of the score. And that's exactly what I did. So you can see that's 30 times P3, which is the marginal probability for the score range 20 to 40, plus 50 times the marginal probability for the score range 40 to 60, plus 70, and so on and so forth. And so basically, no surprises if I look at these mean scores. So basically, the mean score for the midterm was about 70.6. We kind of reported that earlier. And then the standing is 2.9, which means that, basically the class is pretty close to mostly juniors, but it's a little more heavily weighted towards sophomores than it is seniors. Okay, so now we have all of the pieces that we need to compute the covariance matrix. All we have to do to generate the covariance matrix, which is shown here in the blue box, is basically so to implement that definition for the covariance matrix or the covariance for discrete variables, so discrete random variables. So let's come here to this cell. So we need to compute the covariance matrix cell for the score range 20 to 40 and for sophomores. So how do we do that? Well, basically we take the sophomore number, which is 2, minus the mean for the standing in the class, which is 2.9. That's the L18, times the score range here, which we're taking as 30, the median value there, minus the corresponding mean for the class, which is 70.6. And we're multiplying it by the probability for sophomores to get that score range, which is 0.04. And so that gives us the covariance entry 1.5 in this particular location. Okay. And so we basically can do that for all of these different cells. Let's just pick one at random. So here's the seniors. Seniors are coded with the number 4. So we have 4 minus the mean for standing, which is L18, times the midpoint that I chose for the score range of 100 minus the mean, which is L20, and then times the corresponding probability, which is shown up here in purple. That's the probability that seniors will get a score range of 80 to 125. So that's my covariance matrix here. And then to get the covariance, all I do is I sum over all of these scores in the blue box. I sum over the entire covariance matrix. So that just brings me back to the definition of covariance. And so there you have it. There's a covariance of minus 0.456. So that means there might be a negative correlation. But we don't really know until we normalize the covariance. Because the covariance itself doesn't mean much, but when we normalize it by the corresponding standard deviations for standing and score, then we get a number we can actually work with, because we know that varies between -1 and +1. So, so in order to compute the correlation coefficient, which is what we want to calculate last, we need to determine the standard deviation for standing and the standard deviation for score. And so that's what I've done here. I basically have just taken the square root of each of the standing scores minus the marginal probability for that particular, the standing score, in this case 2, minus the mean for that, for the standing, which is 2.9, squared times the probability of, in this case, sophomores taking the exam, plus 3, which is the juniors, minus the standing, which is 2.9, L18, squared, times, again, the corresponding probability, marginal probability for juniors, plus 4, that's the score for seniors, minus L18, the mean for standing, squared, times the probability that seniors took the exam, or the marginal probability for standing for seniors. And so, and then that would be the variance, and then I take the square root of that, and I get the standard deviation. And so I basically do the same thing for calculating the standard deviation for the score. I won't bother going through it. I think it's pretty obvious if you look it over. So basically that gives me then the standard deviation for standing and standard deviation for score that I need to compute the correlation coefficient, which then is just the ratio of the covariance and then the product of these standard deviation for standing and score. And so that's what I've got. And when I finally work that out, I've got a correlation coefficient of minus 0.02969, blah, blah, blah. So basically, anything that is less than about plus or minus in magnitude, less than plus or minus 0.5 is probably a very weak correlation. And this is an extremely weak correlation. 0.02 or minus 0.02 or 0.03 is essentially no correlation at all. That's just noise. And so based on this, we would conclude that the random variables standing and score were actually statistically independent. It really didn't matter if you were a sophomore, junior, or senior. You had just as likely a probability to get any one of these score ranges. That probably just depended on how hard you study, right? And that would be great if we knew how many hours you studied, because then we can include that as the third random variable. But maybe that's going to be a study of itself. The other thing that I did, I want to come back to the presentation for just a second, and then we'll say goodnight. Okay, so let me just come back to the presentation. Okay, so I'm going to come down to the very end. And I shared, actually, so relative to this last question, I thought I would show you what an uncorrelated distribution set of random variables looks like. So what I've done is I've basically taken all the scores, exam scores for sophomores, juniors, and seniors and plotted them here. And so you can see that, in fact, there really is no obvious correlation. So if this, say there was a positive correlation between exam scores and standing, you would expect that for sophomores, the scores would have clumped down here in the, say, less than 40 range. Maybe in juniors, they would have clumped around 60 to 80, and then seniors would have been up here around 120. That would have been evidence of a very strong positive correlation. Conversely, you can imagine that maybe, maybe it goes inversely with age, and so sophomores are really good at studying, and so they get all the high scores. So all the scores would be up here for the sophomores. Juniors would be getting dumber as they get older, and then seniors would be like, "Get me out of here," and they don't want to study at all, so they'd be down here. That would be a very strong negative correlation. But you can see we don't really have either a strong positive correlation or a strong negative correlation. All we have is essentially a shotgun where really there's almost an even distribution of scores across the sophomores, juniors, and seniors. Okay, so that's all I had to share tonight. Sorry about the fire alarm, but hopefully you got the idea, and thanks for listening.